A storage account is the administrative and security boundary that provides a unique namespace for data services in Azure. Think of it as the container that holds endpoints for blobs, files, queues, and tables, along with shared settings like networking rules and encryption defaults. This matters because decisions made at the account level, such as redundancy or firewall posture, cascade to everything inside. Picture a team hosting logs, user uploads, and application artifacts in one account. A single misconfigured public network rule could expose more than intended. A misconception is that more accounts always mean better isolation. Too many create key sprawl and tangled policies. Practical guidance is to align accounts with lifecycle and compliance needs, grouping data with similar sensitivity and retention. When the account boundary mirrors how the business manages risk, operations stay clear and audits become straightforward. Azure Storage offers 4 primary services: Blob, Files, Queues, and Tables, each solving a distinct problem. Blob Storage is for unstructured objects like images and backups. Files provides network file shares for lift and shift scenarios. Queues enable reliable message passing between components, and tables deliver schemaless key attribute storage for lightweight, scalable lookups. Choosing among them matters because performance models and APIs differ. Imagine an image-heavy website. Placing thumbnails in blobs, configuration share in files, and asynchronous resize commands in queues keeps each task in its sweet spot. A misconception is forcing everything into one service for simplicity. That often inflates cost or complexity later. Map each workload to the service that naturally supports its access pattern. By letting services do their best work, you build a platform that remains nimble as features evolve. Within Blob Storage, blob types control how data is written and read: block blobs, append blobs, and page blobs. Block blobs handle most objects by assembling data in blocks for efficient uploads and parallel transfers. Append blobs are optimized for log-like scenarios where new data is always added to the end, making them ideal for telemetry streams. Page blobs support random read and write on fixed-size pages and back virtual machine disks where low-latency seeks matter. This matters because selecting the wrong type can hinder throughput or complicate updates. Picture an analytics pipeline writing events to append blobs while storing static assets as block blobs. Each action fits its pattern. A misconception is that page blobs are always faster. They solve a different problem. Choose the type that reflects how your application writes and retrieves bytes, and you'll keep performance smooth and predictable. Access tiers, hot, cool, and archive let you trade retrieval speed for lower storage cost over time. Hot tier is tuned for frequent access with low latency. Cool tier lowers cost for data read occasionally. And archive minimizes cost for rarely accessed data with hours-long rehydration. This matters when data ages from active to historical and you want pricing to mirror that journey. Imagine product images staying hot for a launch month, then cooling when traffic settles. Lifecycle rules can move them automatically. A misconception is that archive is a perfect backup replacement. It is cost-effective, but retrieval time and minimum retention fees require planning. Use tiering deliberately, defining when data cools or archives based on business events rather than guesswork. Well-chosen tiers keep your storage bill aligned with actual value. Performance tiers, standard and premium, address the need for throughput and latency at different price points. Standard relies on cost-effective media suited to most workloads, while premium uses faster solid-state storage to deliver higher input and output operations per second and lower latency. This matters for scenarios like virtual desktop profiles or transaction-heavy metadata where sluggish I/O becomes user-visible. Picture a content platform keeping thumbnails on standard but placing a hot metadata index on premium for snappy lookups. A misconception is upgrading everything to premium just in case, which overspends without measurable benefit. Profile your workload, measure bottlenecks, and place only the latency-critical paths on premium. By matching performance tier to real need, you spend where it moves the needle and save where it does not. Redundancy families determine how many copies of your data exist and where they live: locally redundant storage, zone redundant storage, and geo-redundant storage. Locally redundant storage keeps multiple copies within a single data center. Zone redundant storage spreads copies across availability zones in a region, and geo-redundant storage replicates to a secondary region for disaster recovery. This matters because durability and availability expectations vary across datasets. Imagine regulatory reports stored with geo-redundancy for regional incidents, while transient caches sit on local redundancy to control cost. A misconception is assuming the strongest redundancy is always best. Right patterns, recovery objectives, and budget shape the right choice. Pick a redundancy model that satisfies recovery goals without unnecessary replication overhead. With clarity here, you design resilience instead of hoping for it. Security for storage rests on two pillars: encryption and identity. Encryption at rest protects data even if underlying media is accessed, and encryption in transit secures it over the wire. Identity ensures that only authorized principals gain entry, replacing static secrets with roles and time-limited claims. This matters because storage often holds the most sensitive business assets: customer files, keys, and records. Picture enabling default encryption and enforcing client connections over secure protocols, while granting applications access through managed identities instead of shipping keys. A misconception is that encryption alone solves exposure. Weak identity or open networks still leak data paths. Combine strong encryption with least privilege access and clear audit trails. When both pillars are present, storage becomes a trustworthy vault rather than a hopeful container. Access methods define who can use storage and for how long: account keys, shared access signatures, and role-based access control. Account keys are powerful root secrets that unlock almost everything. Shared access signatures grant scoped, time-bound permissions to specific resources. Role-based access control assigns rights to identities at precise scopes. This matters because handing out broad keys is simple but risky, while short-lived tokens and roles align with least privilege. Imagine generating a shared access signature that allows uploads to a single container for 15 minutes, keeping the rest of the account off-limits. A misconception is that rotating account keys is enough. Leaked keys still expose the entire surface. Prefer identities and scoped tokens for applications and use keys only where unavoidable. That shift turns access from permanent secrets into controlled, auditable intent. Networking controls determine whether clients reach storage through public endpoints, restricted ranges, or private addresses. You can confine access to selected networks, require traffic through private endpoints, and pair these choices with firewalls and routing to keep data off the public internet. This matters when auditors ask for proof that sensitive information never traverses open paths. Picture a web application that reads from storage only over private endpoints, while a central firewall inspects outbound calls. A misconception is enabling a private endpoint and forgetting domain name system, causing clients to resolve public addresses anyway. Validate name resolution, review effective routes, and test from real hosts. When networking and names align, private connectivity becomes a reliable habit rather than a fragile exception. Lifecycle management policies automate the movement and cleanup of data over time. You can transition objects between access tiers, delete old versions, and expire stale files based on rules tied to age or tags. This matters because manual cleanup rarely keeps pace with growth, and yesterday's hot content becomes today's archive. Imagine setting a rule to move logs to cool after 30 days and delete them after a year, keeping only what audits require. A misconception is treating lifecycle as a one-time setup. Evolving retention needs and new data classes deserve updates. Start with conservative rules, observe usage, and refine thresholds. Automated lifecycle turns storage from a static attic into a living archive that reflects real value. Monitoring closes the feedback loop by tracking capacity, transactions, and latency in one place. Capacity tells you how fast data grows, transactions reveal access patterns and potential throttling, and latency hints at network or design issues. This matters because surprises show up first in metrics long before users complain. Picture a dashboard where sudden transaction spikes identify a runaway script, or where latency jumps after a routing change. A misconception is watching only total size. Transaction volume and error codes often tell the true story. Instrument storage with logs, set alerts on unusual patterns, and review trends in regular ops meetings. With consistent visibility, you steer instead of react, keeping storage healthy as applications evolve. Costs arise from more than gigabytes at rest. They include tier selection, operation counts, data egress, and replication choices. Frequent small operations may outweigh the price of raw capacity, and cross-region reads or internet egress can dominate bills. This matters when a well-meaning design uses chatty patterns that look cheap on paper but expensive in practice. Imagine batch writing larger blocks less frequently, caching read-heavy content, and keeping data in region to minimize egress. A misconception is that cheapest tier always wins. Slow retrieval or minimum retention fees can negate savings. Model cost with real access patterns, then tune tiering, batching, and locality. When you align architecture with pricing mechanics, spend follows value instead of accidents. Choosing storage with intent means matching data characteristics to services, tiers, redundancy, security, and cost controls you can sustain. Start by naming what the data is, who touches it, how often, and how fast it must return. Map those traits to the right service, select a performance and access tier that fits, and anchor the account with the redundancy and networking posture your risk profile demands. Prefer identity over keys, automate lifecycle, and watch telemetry like a pilot watches instruments. A misconception is treating storage as something you set once. It is a living part of your platform. With mindful choices and regular review, Azure Storage becomes a steady, efficient foundation that supports everything you build.